Welcome back to this series of lectures on thermodynamics. This is an interesting video on the first law of thermodynamics, and it is about Joule's experiment. Joule's experiment is an important experiment. It is actually not a single experiment, but we would be looking at it as if it is a single experiment which was performed. So Joule's experiment is a set of experiments conducted by the scientist physicist Joule to demonstrate the first law of thermodynamics. It's a very interesting setup which he designed, and I would not be going into much details. The objective here is to simply give you an overview of this experiment. So if you want to understand really what first law of thermodynamics is, it starts with the demonstration of what is known as Joule's experiment. Before that, what is the finding of the Joule's experiment that I would like to introduce to you, and then we would go to the experiment proper. So that would be the plan of the lecture. So the objective is to clearly demonstrate the first law of thermodynamics using the Joule's experiment, which is the experiment which demonstrates the first law for a thermodynamic cycle and for a very specific system, namely the closed system. You must be remembering that closed system is a thermodynamic system which does not allow any mass transfer. It is allowing only the energy transfer across the system boundaries. And after we explain this and understand this experiment for a thermodynamic cycle, we would also look at the mathematical statement of first law of thermodynamics for a thermodynamic process. So what is that statement which is to be proved using Joule's experiment? So read this very carefully. It is applicable to a cyclic process. The statement is applicable to a cyclic process and to a control mass. By control mass, we mean it is a statement applicable to a closed system. That is, there is no mass interaction between the system and the surrounding. So what does this system say for a control mass undergoing a cyclic process? The statement says that the cyclic integral of heat is proportional to the cyclic integral of work. Okay, so obviously when I'm using the term cyclic integral, I'm referring to a thermodynamic cycle. And when I'm saying the term is integral, it means that summation of all the heat transfer in the thermodynamic cycle. Similarly, when you are saying the cyclic integral of work, it means that summation of all the work transfer in the thermodynamic cycle. What is to be understood before we demonstrate the Joule's experiment is both the heat transfer and work transfer, they have a very specific meaning when we are talking with reference to thermodynamics. Heat transfer is an energy transfer across the system boundary. Similarly, work transfer is an energy transfer across the system boundary. The difference between the work transfer and heat transfer is as follows. Heat transfer would happen only if there is a temperature difference between the system and surrounding, whereas work transfer happens across the system boundary without even if there is no temperature difference. Okay, so we can define the heat transfer in thermodynamics as the energy in transit, energy transferred across the system boundary because of temperature difference. Work transfer can be defined as energy which is transferred across the system boundary without any temperature difference. Now, to prove this, that the cyclic integral of heat is proportional to the cyclic integral of work, a very interesting arrangement was chosen by Joule's. So if you look at this diagram, what is clear to you is that the Joule's experiment comprised of an insulated container. A container was used with a fixed quantity of water in it, and that container was insulated. When we say it is insulated, what it means is that there is no heat transfer across the system boundary. Okay, and hence it is a and because the container is a closed container, it is a controlled mass, it is a closed system. So this system, when it is insulated, would allow only one form of energy transfer across the system boundary, and that is the work transfer. Why is the heat transfer not allowed? The heat transfer is not allowed because the insulated is kept, the vessel is kept insulated, the container is kept insulated. So what type of work transfer was performed during the Juice experiment? So in the Juice experiment, Joule used the paddle wheel arrangement to perform paddle wheel work on the water which was enclosed in the container. So a very simple arrangement of performing a paddle wheel work is shown in the figure. You see over here that there is a pulley arrangement. Okay, there is a string which has a weight attached, and by lowering the string, by lowering this weight, one can have this shaft rotating and performing stirring action. So this work, when you are having a lowering of this weight through a particular height, what would happen is that there would be a work transfer to this working fluid. The working fluid here is water. So Joule performed work transfer, and as a result of which this system, let us say that this system was initially at certain state 1. State 1 means this system was having, let us say, a certain temperature T1. Okay. And then when the work was transferred to this, obviously there would be some change of the state. So let us say that state initially was state 1, thermodynamic state 1, and because of the work transfer, there is a thermodynamic process, and if we get another state, another new state, namely the state 2. So why has this process happened? Why has this system changed from state 1 to state 2? The system has changed from state 1 to state 2 because of work transfer W12. So this is a part of Joule's experiment. So in the first part, the Joule's experiment is about work transfer W12. In the next part of the experiment, what Joule did was he removed the insulation. So when he removed this insulation, obviously what would happen is that when there is a insulation being removed, there is now a possibility of heat transfer. Okay, so he did exactly the same thing. When he removed the insulation, this water which was now at a higher temperature, some T2 temperature, okay, it it started interchanging, it started exchanging the heat with the surroundings. Okay, and as a result of which now there is a heat transfer from this water, that is the control mass, with the surrounding which was at a temperature T1. Okay, so this system now would come back again to the initial state 1 because of the heat transfer Q to 1. So why has this heat transfer Q2 to 1 happened? This heat transfer Q2 to 1 has happened because the insulation was removed. And what was the finding? Okay, what did he do? So initially he applied certain weight W and he measured this work done. How did he measure this work? He measured this work done as mgh. M is the mass of this weight, G is the acceleration due to gravity, and H is the height through which this weight was lowered. Okay, so this is how he measured W12. How did he measure Q12, Q2 He measured Q2 by noting down the temperature which was recorded by a thermometer. You see that there is a thermometer over here. So what does this thermometer note? This thermometer notes the initial temperature T1 and the final temperature T2. And he knew the mass of the water which was kept in the container. So the mass was known, the specific heat of water was known, and this temperature was known. So mcp delta T, mass into specific heat into change in temperature of this water because of work transfer, gave us Q2 So he noted down this value of W12 and he noted down this value of Q2 Okay, this kind of experiments, he performed such n number of experiments with different masses, okay, and with different quantities of water. And what he found was that there is a certain relationship between the work transfer and heat transfer. Okay, and that relationship was applicable for a thermodynamic cycle, and that is what is the first law of thermodynamics as applied to a closed system undergoing a thermodynamic cycle. What is that? That cyclic integral of heat transfer is always proportional to cyclic integral of work transfer. So whatever you do, whichever way you transfer the heat and work, okay, for a closed system, one can show that the cyclic integral of heat transfer would always be proportional to cyclic integral of work transfer. This is the law of nature, and it can be described only for control mass. So what is the proof of this? There is no theoretical proof to this. There is only an experimental evidence. Okay, one can perform this experimental experiment and one can prove this. Okay, so this is about Joule's experiment. I hope you have understood the Joule's experiment, and if you have understood this, we will go to the next important statement, a very brief statement for what is known as the first law of thermodynamics as applied to a closed system but undergoing a process. Right now, to understand that statement, we would only look at the first process, that is 1 to 2. When you look at the process 1 to 2, okay, only a thermodynamic process 1 to 2, we would imagine what happens to this work. Okay, when you are transferring this work and when the system is insulated, right, what happens to this work, where this work disappears? So the work does not disappear, mind well. What happens to this work is that this work is transferred to this control mass, as a result of which its internal energy increases. So the first law of thermodynamics as applied to a process 1 2 would be W12 would be equal to change in internal energy from 1 to 2. Okay, so W is equal to delta E when you are applying the process 1 to 2. Now, if you imagine the process 2 to 1 only, forget about the process 2 to 1, what you find is that the internal energy now decreases, right? And there is heat transfer. So Q now is equal to delta E. So the general mathematical statement for a thermodynamic process, not for a cycle, mind well, is Q is equal to delta E plus W. Q is equal to delta E plus W. So mathematical statement for a thermodynamic cycle is cyclic integral of del Q is equal to cyclic integral of del W. Whereas mathematical statement for the process, thermodynamic process, is Q is equal to change in internal energy plus work transfer. Q is equal to delta E plus W. Thank you very much.